Okay, so now the last part of this session, checking consistency in parametric interval Markov chains. You've seen parametric interval Markov chains model, checking consistencies for IMCs, and the consistency problem for parametric interval Markov chains is the following. The question is, does there exist a parameter evaluation V such that the IMC, the corresponding IMC, is consistent? And is the IMC VFI consistent for all parameter evaluations V? And we want to compute all parameter evaluations such that the IMC is consistent. So let's see how we can check these in parametric interval Markov chains. The problem is decomposed into several parts. The first one is local consistency constraint for state with respect to some subset of states that are the successors. As you've seen before in interval Markov chains, we are trying sometimes to avoid some successors that are not making the model consistent. And so we'll look at consistency, local consistency, with respect to a set of states that we want to reach. So local consistency is expressed here for a state S and a subset of states S prime of successive states. And we want to check that the sum of the upper bounds of intervals going from state S to its successors that will remain is greater than 1. So that's exactly what we did for IMCs before. And that the lower bound of the arcs going from S to S prime is smaller than 1. So for all arcs that remain in the model that we'll use, we have these conditions on lower and upper bounds. But also we want to be able to avoid these states that are not in S prime, that we'll see afterwards. And we have to check that the lower bound is smaller than the upper bound. And that will be important. That was not really something we looked at in the IMCs, but it will be important because we have parameters. And so we'll have conditions on parameters there, saying a parameter, if it's a lower bound, it must be smaller than the upper bound. Now, the inconsistency constraint for S is given according to a set of cutoff successors. So let's let X be a set of successors. We want the local consistency to be valid for S and the successors except those you want to avoid. And also that here all lower bounds going from the state S to a state in the set you want to avoid are 0. Okay? So that is for 0 consistency, and for n consistency you will check the same thing for the the local consistency. You will also check that everything you want to avoid can actually be 0. And you want to check that all successors that you are keeping are n-1 consistent. The n-consistency constraint for a state S is expressed as the union on all possible subsets of avoidable states of this constraint. Okay? So the difficulty here is that you have a set X of states you want to avoid, but you don't know a priori which ones are really being avoided because you have parameters, so you have to play with them. And maybe you want to avoid one successor or two successors, and you have to take into account all possible cases. So the consistency of a PIMC is such that a PIMC with n states and an initial state as 0, if we have a parameter evaluation V, VFI is consistent if and only if V is satisfying the consistency condition for S0 at level n. So let's see an example. We have the same example as before with parameters P and Q, and if you do the computations, you'll find that the result of the computation is an expression. Here it's given here. So this equation is what you obtain after applying these consistency equations that I just showed before. You see that this PIMC is consistent if Q is between 0.3 and 0.7, or if Q equals 1. And there's no condition on P. Whatever the value of P, this is correct. And actually, there are two different parts in this, in this formula. So the first one, Q is between 0.3 and 0.7, corresponds to the part of the PIMC that is here. So this part. And the other possibility, Q equals 1, corresponds only to this part. So you can see it's two different choices in where you go in the model. On the one hand, it's the upper part, and the second Q equals 1 is the lower part. And that is the reason for which set of states, X, am I going to avoid, and that gives complexity because either you choose to go in the upper part of the model here or in the lower part of the model. So here you know about parametric timed automata, their problems and algorithms. You know about interval Markov chains with parametric probabilities, and in the next session you will practice with imitators and PTAs.